think that's the only way I can figure it out.
I barely noticed it. Because we can't. Because NASA is, and I'm arguing from their point of view in the debate. Wait, you're going to? You're not going to Mars?
Oh, that was great.
Well, our argument isn't that we should go to Mars. Like, I'm not saying that we should go to Mars. I'm not saying that we should or shouldn't go to Mars.
Okay, so we have two sections today we're going to cover, 6.2 and 6.5. The first one, 6.2, is on area. We spent time, obviously, calculating area underneath one curve. Now we're going to find area between two curves or more. And then the second one is on arc length. We'll get to that in a moment. So, 6.2, area between two curves. Well, let's just say area between curves, because you could actually have more than two. And this is on page 445 in your book. So, first of all, just to recast, this is f of x. We know if we were finding this area under f of x, between f of x and the x-axis, and between a and b, that we would use the definite integral. Okay, so we've been doing that. That is equal to this area. Right there. Now we're going to talk about, well, what if you had more than one curve? What if we have here the area, for example, between two curves?
Mr. Guy, can you scroll back up that screen just so I can see the graph?
We're trying to break into the...
That's so aggressive.
It's locked.
Oh.
Yeah, you try to barrel in.
Put the safety latch on there so nobody gets hurt.
It is locked.
All right, good job. We're all right? Good? You got that?
Yep.
All right, so two curves. There's one curve. We'll call that f of x. And we'll do another one like this. We'll call that g of x. And we want to find this area right there. Any ideas? What do you think? What do you think?
Could we do the absolute value of f of x minus, the integral of f of x minus integral of g of x?
You got the right idea, because you think about it, two areas like f and g, and we're subtracting. Yeah?
Well, you could find the overall area subtracted.
Yeah, but look what I did to you. I put it part of it below the x-axis. That's, you know what I'm saying? We just had, like, if this f of x crossed, remember we had to do something different and all that stuff. So, yeah.
I don't know, would it be like the absolute value of both, or like the integral of each function minus the integral of the absolute value of each function?
You all have some great thoughts, and they're all saying the same thing, right? Somehow we have to do some sort of subtraction going on back there. Peter?
Treat g of x like your new x-axis, kind of.
Okay. All right, no, that's all right. Keep going. All right. Here, so let me show you conceptually how we want to think about it. Remember when we just had area under one curve? We made the boxes. We did Riemann sums. We talked about how they approximated that. So think about that same concept here. If we divide this into subintervals, into these rectangles, and we found the area of each rectangle, and then we added them all up as the width of the rectangles approached 0 or the number approached infinity, then we'd have it. So let's just look at the area of one box. We know the area of a box is going to be in this case, the height of the box times the width of the box. Well, the width of the box, that's not changing. We've always talked about that being delta x. That's how wide they are. But height, and don't worry about the left side or right side or anything, just in general, if I want to find the length of this between these two equations right here, how do you find out how long something is?
Top minus the bottom.
Nice. The top minus the bottom. We want to just subtract. We want the bigger value minus the smaller value. Always. Doesn't matter where it is on the x-axis. If it's above or below, do we have to change anything else? No, Mr. Guy. We wouldn't need to do that, right? If this was 5 and this was -7, 5 minus -7 is 12. That's how long that is. Okay? So, for this problem, this area, the height is just f of x minus g of x. And again, that is one box. And it would be the integral that would add up the area of all the boxes. And so you can see how you're going to get f of x minus g of x. Regardless of where it is, doesn't matter if it's above or below or combinations are crossing over, it doesn't matter. In general, you just want to make sure you're doing the integral of the top minus the bottom. All together as one integral. Some people like to separate them into two. It just, to me, why would you do this? Ends up kind of always being extra work. You put them together, simplify and integrate, you're going to be fine. Yeah, Bailey.
Do the absolute value in the order in which they agree with matters.
So you're thinking, well, what if I wasn't sure? What if I made a mistake and I had the wrong one on top, right? Yeah, so if you do everything right except you do bottom minus top, the worst thing is going to happen? What will you get for an answer? Right, and but it'll be just the exact opposite of what you wanted, right? And then yes, you could go ahead and take the absolute value of that, but you just have to make sure that you got a negative answer because your only mistake was the order that you subtracted, not because you made some kind of mathematical mistake in your work, and sometimes that can happen.
Could you just avoid it by doing absolute value of top minus bottom, or would that not work at all?
I would not avoid it. I would know which one's top, which one's the bottom. Because as you're going to see in a moment, they could cross over. And if you didn't actually look at the graph, then you're going to be really in trouble. Okay? So, top minus bottom, yeah.
Well, I guess that was my next question. Is that if you had to find the area past where they cross over, do you have to do two different integrals?
Yeah, let's think about it. Boy, that's my next graph here. Let's draw a picture of that.
I was just thinking.
No, it's great. I'm glad you're thinking. So let's say this is f of x, and this one's g of x. And maybe we want to, wait. Jeez, I almost forgot. Can I back up for a moment here? Sure. We need limits. We can't just take the integral. We got to go from a to b. I want to make sure you get that in your notes. A is there and b is there.
So it's just where the area starts and stops.
Yeah, if they don't tell you start here and stop there, and they just say the area that's enclosed by these two graphs, bless you, you need to figure out those points. How are you going to, they won't necessarily tell you what that is. How are you going to find out that point? So you would set them equal to each other, go back to your Algebra 2 skills, and solve that system of equations and find out those points.
Or if you're on our calculator, we can just use that then too.
If it's the 1/4 of the test that's calculator active, yeah. Okay, so don't forget, you will have limits. You'll need to figure those out. Same story here. Let's say that they're going to tell you to go from here, A, to maybe here, B. So we have this area defined. And then Dave, what were you saying? What do you think would be the approach to?
We have to find where they're cross.
Yes, we would have to find that. So we would again set them against each other. So let's call that C.
That would take two different intervals.
So from A to C, and the top here is f of x minus g of x, and we would add it to from C to B. This now the top is g of x minus f of x.
Oh, so you like whatever like function is on the top.
Top minus bottom. Top minus bottom. Don't forget that. That's so important. See what it looks like and figure out which one's on top, which one's on the bottom. If you don't look for that, like if you just said find it from A to B, you can see how people just flat out take the integral. When they're done, take the absolute value and think they got the answer, and that's wrong. Because it won't work out to be the same unless you break it into two pieces. Yeah.
How do you know which one is the top and which one is the bottom? Necessarily, because like if
You got just the graph.
if you saw like only a section of like C to B, you might think that G of X is the top one.
You need to see the graph for the entire interval that you're trying to find the area.
Okay, so then it's just based on the interval that you're seeing. It's top and bottom.
Yeah, right. Like I don't really care. These might cross over multiple times. It doesn't really matter. It happens over there. I just need to see between A and B. Okay, good.
You have to break this one up?
What's that?
Why do you have to break it to two?
Well, why would you not?
What's on top switches?
You understand how you'd have a problem there? Yeah, because part of it cancel out, and then even if you took the absolute value, you're still not going to get the right answer.
Like this is the
Perfect. Okay. Now, some people at this point usually wonder themselves, why are we doing anything different for two equations than we did for one equation? Why is it all of a sudden something special? And it's not, but we just never thought of it this way before. So when we go back to looking at it one equation, we really had two equations here, because we always said the function and the x-axis. What's the equation of the x-axis? 0, right. So this would be technically f of x minus 0 is what you're finding there, but we just don't do the minus 0. That's why it is really the same thing. It's the area between two defined functions. And on top of it, the same idea of like, well, why did we have to break it into pieces before if it crossed the x-axis? The same story here, A, B, and C. We're finding this area because here, this is f of x, that's on the top, and now 0 is on the top here. So this would have been from A to B of the top, f of x minus 0, plus from B to C of 0 minus f of x. And again, I think that's kind of helpful to see why that works out. You can tell how you're going to get the opposite of that right there. Okay? Let's do some examples. Let's say f of x is x squared minus 4x plus 10. And g of x is equal to 4x minus x squared. And we want to go from 1 to 3. Find the area. So you should always sketch a graph for these. There's a chance that you'd have to graph things by hand. So, especially if it's linear or quadratic. Usually not much beyond that, but they want you to sketch it quickly by hand. This bottom equation here, you can tell that it's going to cross at the point 0, 0, 1, 2, 3, 0, 4. And it's a frowny face parabola, so we go like that. In the other one, quadratic equation has a y-intercept. Well, it's not really drawn on scale, but at 10. And that one's going to go like this. And it said from 1 to 3, because this right now there's no defined region. For a lot of people, it's the hard part is figuring out what is that region. So 1 to 3 So here we are. That's our area. Okay, and this is pretty, laid out nicely for you. That doesn't cross over anything. You just have the integral. And they told you what the limits are, 1 to 3. Your top equation is the smiley face quadratic minus the whole other quadratic. And as you can imagine, this is where people run into a problem there. So it's minus the whole thing. Make sure you distribute that all the way through. In other words, a little bit more here. X squared minus negative x squared becomes 2x squared. Minus 8x, 10. And then keep going. We're going to not keep going in the notes just to save time. You all know how to do integrals. You know what to do. You would, I think on this one, you actually get 16/3. You want to check your math later on or something.
So
Any questions at setting that up?
So after like plugging in the limits, you're supposed to get like 16 like that.
Yeah. Don't write keep going on your tests, okay? Please don't do that. I'm just trying to cut some time out of notes here to give you some work time, okay? We don't need to do them all up. All right, let's do another example. F of x equals x squared minus 5x minus 7, and g of x, x minus 12, and they're going to give you the interval from -2 to 5. They don't always give you the interval. Sometimes they just say the area bounded by those, and that's where you have to use or work with the points of intersection. So this thing, you got a quadratic, you got it crossing. This would be -7 here. It's going to look like that. And then this equation, it's going to look kind of like that. So if they didn't give you the interval from -2 to 5, it really just comes down to this little piece down here. That's the only place that's bounded by the 2. Like, the hardest part for people is to figure out, well, which area am I finding? And you got to think, which one has lines or boundaries all the way around it? It's like coloring. You got to stay inside the lines. Like if you started shading in here, well, you just keep on going on forever. And not up here, you go on forever. And over there, you go on forever, and so on. So if they didn't say -2 to 5, you really would be just looking at this piece right there. But now they have these other limits. It's like saying these are like other graphs or lines. So -2 is over here, and that would be, I didn't really draw this to scale much, but let's say -2 is right there. So that gives you this other piece here, and it just turns out that that hits exactly at 5, so we don't have to do anything beyond that piece. Now what they didn't tell you is where they intersect. So of course you'd set them equal to each other and solve. We'd set those two equal to each other. That equals that. We'd subtract -6 plus 5, -1 and -5, right? So it's going to be, so this is -1, this is 1 right here. In other words, x minus 1 times x, like you would do all that work, you get it. Alright, so we just found that point. Alright, so -2 to 1, top here is the quadratic, x squared minus 5x minus 7, minus the bottom, which is the linear, put parentheses around it, plus the other piece, from 1 to 5, top is the linear, minus the bottom. And then go from there. It is interesting, on some of the problems on the AP exam, let's say just set it up, and you don't have to actually take the integral or figure it out. That does happen occasionally. Not too often, but once in a while. All right, so that's just one crossing over. We already talked about that. Here, let me give you another one that's a little more exciting. Let's throw 3 equations in here now. So we're going to go f of x, g of x, h of x. And we have the area in between here. Looks like the, what's the starfish's name in SpongeBob?
Patrick?
Yeah, doesn't that kind of look like?
Looks like a crane.
What?
Stingray.
He doesn't have
Oh.
legs.
Yeah, it doesn't have
I
legs.
can't see the bottom part.
Anyway, that's what we're going to find, the area, okay? All right, so if you're not too sure, think about making cuts into it, boxes to find the top and bottom. We start cutting up Patrick like that, and we end up, we got a problem. We're going to have a problem. Top is f of x here, bottom is h of x, and we get to right here. What's our problem? Yes, the top changed. So what are we going to have to do? Call those two guys. It's okay. Yeah. Yeah. Yep.
The thing is, you're not looking at it.
That was just
We're not sure what's
Yeah, bush.
Actually, no.
You know who didn't look that bad after he was done?
Sure. Yeah. So just let you get, in terms of.
Well, I mean, he died, so he had the worst thing. Kenny Lincoln had the worst thing.
Lincoln actually had some really big chambers. Like, he came in all this jam. He's kind of gone. That's by the end.
Well, the only reason he had a beard was because such a little girl wrote him a letter saying he looked better.
ignore me advice today.
Yeah.
And that's also a little
I gave
bit
that
read
to
a
her.
letter from
So
someone
I know.
else. Also the reason we have Thanksgiving.
All right, great.
They should have written more letters.
To the president. Who is the president of India?
So, are we all good with this? You seeing how this is going to work? Integral, and I don't know, we'll call this A. We got to figure out B and C. So, from A to B, the top was, what was that, f of x, and this is h of x. So this might happen sometimes. This is why you have to look at the picture. You can't just assume, I'll just throw it in there and it'll all work out. You have to know exactly where you got to break it apart and what's on the top, what's on the bottom. Got it? That's how I knew to break it apart, because my top, if your top or bottom changes, then you have to start over and you're going to make a new integral. So what, I'm sorry, what? I heard somebody,
So just like with the
Yeah.
going, you just take the integral of like when you're like
top minus bottom.
simplifying.
Yep. Oh yeah, keep going, yeah,
Keep
sorry.
going, like,
Yeah,
simplify and
just
take
keep
it.
simplifying all the way down, then do the usual story, integration, plug the numbers in, that's it. Okay, let's do another one. It's a little bit more exciting than that one.
Stop plugging numbers. I should write that out. It gets so confusing.
Okay, so this one's different.
Yeah.
These are functions not of x, but of y. Alright, so first of all, that's weird. So they're not functions where you would think of a function, like they wouldn't pass the vertical line test because they're functions of x with respect to y. In other words, this would be another way of writing this equation. X equals y squared minus 1. X equals y squared minus 1/8 y to the 4th plus 1. And you'd want to sketch the graph of those. So, if you had to do it by hand, you would probably have to start plugging points in and seeing what happens. And if you did it on your calculator, we'll talk about how you might try to approach that. This is a parabola. This is has an x-intercept of -1, so this is a sideways parabola like that. And then this is a 4th degree. When you start plugging in points and see what happens there, this is going to look like that. And you're finding the area bounded by those two equations, two curves, which is this stuff right here. I think it kind of looks like the Star Trek symbol on the side. Oh, you think it's...
Or a boomerang.
I think it's supposed to be a little funny. Yeah, a boomerang would probably be good.
My drawing was like a line being that size.
Yeah. Everybody's drawing will look different. Even though they should be exactly the same. Okay.
Not the scale.
Yeah. We got a problem. If we start looking at this, right away you think, what's my top, what's my bottom? So if you start putting boxes in here, bless you. What's our problem?
The functions.
Yeah. Top and bottom are the exact same equation. You can't, if you took the integral of f of x minus f of x, what are you going to get? 0. That's not right. So, any ideas?
We could chop it in half.
Nope.
and
Don't
make
do that. Yep.
Trans.
You can't just change it. You can't, there'll be different equations. Yeah.
Can you use like the side?
Yeah. Nice job.
Demonstrate.
Pat, one more time. What'd you say?
Use the side. Like,
Yeah, let's cut it like this instead. We're going to cut it like that. Here are our boxes like this. So there's one box right there. Find the length of that box. Now, first of all, the width is changing. What would you now call that? Yes, delta y. So there'll be a dy problem.
Is that a Y?
Is this a y?
Yeah.
This is just like an arrow. So this is delta y. Okay. And then how do you find out how long this box is?
Their X. Subtract.
How do you find the length of things?
top and bottom.
Otherwise known as right minus left, right? We're just subtracting. We're going to find out how long something is. Think of it like a number line. 7 minus 2 would be 5. That's how you find out how long things are, okay? You subtract. So this is going to be right minus left. And yes, you want to draw the picture, and yes, you want to know which one's on the right and left-hand side. You don't just want to randomly subtract them and then hope if you take the absolute value, you get it right.
And then, is there limits with this one too?
Yeah, oh yeah, definitely. Good question. So this would be, just like before, we'll call that A and B, but what do you notice about those values? What kind of values are they? They are y values, correct. They have to be because we're integrating with respect to y. And you have to have y's in here. So your equations have to have y's in them. Fortunately, they already do. That's great that they did that way. So there's two things really when you approach this problem you think about. Number one, look at the boxes. If you can't do top minus bottom, then think about right minus left. And number two, if they give you everything in terms of y, it's probably best to do it right minus left because that would be a dy problem. So for this problem, we would have to find these values, and just to save time, I'll tell you after you set them equal to each other, you would find out they're -2 and +2. So we're going to go from -2 to +2, y values. The right equation is this one here with degree 4, so it's y squared minus 1/8 y to the 4th plus 1 minus the quantity of y squared minus 1 dy. And again, distribute, simplify, then integrate, but always simplify. And keep going until you get an answer. We're going back. You should be able to do this one section. You should do all these by hand. Just make sure you keep practicing doing by hand. And the next section, we'll let you do those on your calculator if needed. Yeah?
Quick question. Is there ever a situation where they have a dy function and a dx function, and you have to find the area of limits?
You would never do a problem that you had dy and dx.
Oh.
Yeah.
That's why you count 3 as
Okay.
just 3 dimensions.
Next problem. Or next section, I should say. 6.5. Length of curves. In other words, arc length. This is on page, good question, I don't know, I didn't write it down, let's see. 480. Okay, so we're going to find lengths of curves, arc length. You remember your glory days of geometry, you got 112% or whatever, I'm sure?
Yeah.
Find arc length there, right, of circles. That's all the arc length you could do. Now we're going to find out how to do anything. Find out how long it is from point A to point B. Wow. So in other words, if I trace that in red, we're trying to find out how long that is. And really, you know, if I ask you this question at the beginning of the hour, you might ask me for string. Cut the string, lay it on there, and then measure the string. That'd be about it, right?
Yeah.
But now we're going to find out, and then we hope you don't stretch the string too long because they change the length. Now we're going to learn how we can do this with calculus. By the way, this is the second BC topic of the whole year. So L'Hopital's rule with those exponent problems that we did, that was the first one. And this is the second one. Everything else you've done so far is just AB. So it's an exciting day for Mel. She can actually learn something new today. Okay? So there is a formula for arc length. I'm going to write the formula down first. We're going to then do an example. And then for those people that are curious, which hopefully you all are curious, I'm going to show you where the formula comes from. It might help you memorize it. Okay? So, here we go. The length, L for length, is equal to, of course we're using a definite integral, that's what the whole chapter is on, applications of integrals. And we're going to go from A to B of the square root of 1 plus f prime of x in parentheses squared dx. That's the formula. Not too bad, really. I mean, it looks a little strange. I'm going to show you where, again, I'll show you where it comes from. Basically, they're going to give you f of x. They're going to tell you the limits. You got to just take the derivative, square it, add 1 to it, throw it underneath the square root symbol, and then take the integral. So they're not too bad of problems. The other, I would say for you, good news, most people think this is good news, is usually when that happens, when you get to the point where you get the integral of the square root, you are unable to do it by hand. And then it's typically a calculator active question then. So on the homework assignment for this page, I think there's only one problem you end up being able to do it by hand. The other ones, the only way you can do it is on your calculator.
And that's
Okay?
just the way you showed us to take the integral rates.
Yes. Yeah, what we covered the other day. Perfect. So, let's do an example. Let's say we have y equals x cubed. And we want to find the length from x equals 1 to x equals 3. So we have our formula. 1 to 3 square root 1 plus dy dx squared dx. First step would be to find dy dx, 3x squared. Then we're going to square that and plug it in here. So it will be 1 to 3 square root of 1 plus that quantity squared. Don't forget to square everything. And if you have this long, complicated derivative, don't square, like this. Like I can square that pretty easily, but don't start foiling out this big, huge, long thing, knowing that you're going to have to plug it in your calculator anyway. So this would just be this. And you can see that if you attempted u substitution here, you let u equal what's underneath the square root symbol. Well, the derivative of that, there's nothing to cancel with it. That's not a special one you have memorized. The only way it's going to come out to be something is if whatever's inside here, inside the square root, is something you can actually take the square root of, typically. That's the only way it's going to work out that you can do it by hand. Otherwise, you use your calculator. Don't do this for my own personal health and sanity. This is not equal to 1 plus 3x squared, okay? You cannot take the square root of each of those separately because of that addition sign there. So please, please remember that. Okay, so you're going to use your calculator for that.
Equals 1 plus
Oh, okay.
So you see what I'm saying? Some people just think you just take the square roots of those parts separately. Okay,
Yeah, it doesn't.
so
Are you trying to?
No, I was.
So now I'm going to try to answer the question of why. Why does that equation work? How in the world did somebody that was really smart figured out that you could use that little formula, which is extremely helpful. So, you want to see this? Are there some people that would like to see it? I think it's actually helpful. Some of you are going to go off to, you just got to be honest with you, we don't really do hardly any proofs, in AP. That's just not part of the curriculum. But most college calc classes, you're going to see some proofs and some more than others. I know a lot of you end up going to Mass and they love proofs there. So I think it's kind of nice to see what's happening. All right, so A to B. F of x. The theory is this. Just like we did with the area, we spliced it up into little pieces, in that case rectangles, found the area of one, and then added them all up. We're going to take this arc length, think of it as a string, and we're going to just cut it up into pieces. We're going to find the length of each piece, and then we're going to add them all together to find the length of the whole thing. It does look like a centipede, doesn't it? Alright, so let's pick one of these pieces. Let's just take this piece right here. I'm going to redraw it, I'm going to blow it up, and it's going to look like that. And there's, a little bit of curve to it, even. Let's say like this. But I'm approximating its length by assuming that it's a straight line. And we're going to use that concept of the straight line, the fact it's a straight line, and the concept of derivative, because we know the slope of this line would be the derivative. So the slope would be dy over dx. And then what they do is they use the Pythagorean theorem. So the length of this, the hypotenuse, that length would equal the square root of a squared, which is dx squared, plus dy squared. That's what we start with. We want to start with that and end up with what we have for our formula. Okay? So, if you notice that and the formula, you can kind of see maybe where this would head if this was a 1. So what I want to do is I want to distribute through here a 1 over dx squared. But I can't just multiply by 1 over dx squared. I can only multiply by 1 without changing the value. So what I'm going to do is I'm going to times this by dx squared over dx squared. So first of all, I'm going to think about multiplying it by that. Now that is 1. So that times that would not change the value of this. But this is underneath the square root symbol. So I'm going to actually stick this underneath the square root symbol so I can put them together. The only way you can get them together under one square root if they're both square roots. Okay, so the key to this, the puzzle piece to this proof is, or explanation at least, is to multiply by this quantity right here. The next step, I'm just going to go through every single, instead of skipping some steps here, but I would see this as 2 separate square roots. Okay, so that's equivalent, and that's still equal to 1. And the reason I do that is I can now multiply this stuff in any order. So instead of having this times this divided by this, I'm going to take the original one and I'm going to take this and put it under that underneath over here. And I'm going to do that, you know what I'm saying, the operation in that order. So this would be equivalent to the square root of dx squared plus dy squared over the square root of dx squared. And that's the differential of x, differential y. Remember, we worked with differentials. Oops, not equals there, sorry. Times that. Well, that allows me to put this as over here as 1 square root. I can combine these square roots together, so this would be equivalent to this. Right? Well, this I can write as 2 separate fractions with this common denominator. So I can write it like this. And then, hopefully you're all starting to see where it's going. This is obviously 1. This is just, I can put this as dy over dx, that quantity squared, because they're both squared. And the square root of dx squared would just be dx. Now, technically, I use dx and dy throughout this whole thing, but technically it's, you know, be like delta y and dy, but when we take the limit as delta y approaches 0, or delta x approaches 0, or in other words, the way to add all of them up is to take the integral. I guess this is probably the easiest way for you to understand that. So that was one piece, and when I do the integral, it's the sum of all of those pieces. And that's where it comes from, which I think is pretty cool. All right, here is your assignment, number 19. Like I said, the first section, please go back to doing the integrals by hand unless they specifically say use your calculator. The second section, you'll notice, I think it's just the first problem you could do by hand, I think. And then all of the rest you would do on your calculator. Those are the arc length ones. All right, and this is due Monday, right? No, no school Monday. How exciting is that? Oh, Tuesday's skinny day. So you guys will go over the assignment. And I'll turn around and I'll see you. So I'll see you Tuesday and
Wednesday and Friday.
Wednesday and Friday, right?
3 or 4 days.
Yeah, so you're gonna have, so we'll just be able to get through going over the assignment, I think, on that Tuesday. And then we'll get notes on Wednesday, and we'll go over it on Friday. So I think I told you, maybe you don't know this, we probably guessed it, we will not have a test. Let me just stop this